All right, so today we're going to be we're going to start section 5.1. And I'm not sure exactly what pages this lands on in your workbook. Sorry about that. I don't have it with me, but these are the electronic version of the notes, the blank notes. And it might not line up exactly with your pages, but it still has the same information. So we're going to run with it. Okay. All right, so just like you can add and subtract and multiply and divide numbers, right? Just like you can do that with numbers. We can do those with functions with, as long as we're careful. Like, what are we not allowed to divide by? We're not allowed to divide by 0, right? It cannot be 0. Same idea here. If we know that a function f exists and another function g exists, we can add those functions, we can subtract those functions, we can multiply those functions, and we can divide them as long as the denominator function is not equal to 0. So that'll have some restrictions on our domain, right? Because um, we can't divide by 0. And so the domains of sum, difference, and product is this the domain where both f of x and g of x intersect. So it's the same. The domain of the quotient, after we divide, um, it's the domain of both f and g of x, but it also has that restriction that g of x can't be 0. So if there's some x value that makes g of x equal to 0, then it gets thrown out of the domain, right? Okay, so here we have an example. Find f plus g of 2. And I'm going to pick which one is which. Okay. So right now they're not labeled on what I can see. And maybe they're labeled in your book, and I'm sorry if they are, but we're going to say that this top one is f of x. And that's what kind of a function is that? A linear function, right? And then we'll say that g of x is this curvy one. And what kind of function does that look like? Quadratic. Good. Okay. So if we're going to find f plus g of negative 2, well, what is f of negative 2? F of negative 2 looks like it is negative 1, right? Negative 1 plus what's g of negative 2? Well, g of negative 2 is 4, right? I look at where the x is negative 2 and I look down at the f function and I look up at the g function. So negative 1 plus 4. So the sum of those two is 3. F minus g of positive 2. Okay, so this time I'm going to grab another color. I'm going to go in and I'm going to look at 2. At x equals 2, what's happening to f and g? Okay, so it says f minus g. So f, it looks like, is 7 minus g, it looks like, is 4. So 7 minus 4 happens to be 3 again. Crazy. F times g of 1, new color. So first we're going to look at when x is 1, what's happening. So f looks like is 5. This time it says to multiply that times g, which it looks like is 1. So we get 5. I'm not sure why this is written on here twice, but I mean, that's saying to do it again twice. So I want to change that a little bit. What I am interested in is what happens if you do g times f of 1? Well, you change the order for multiplication, it doesn't matter, right? If you change the order for multiplication, it does not matter. No big deal. Okay. But this time, let's say they don't give you a graph. Let's say they give you two tables, like up here in the top part of up here. And then they ask you to do a whole bunch of things. Okay, same idea though, right? So we're going to figure out what f of negative 2 is. F of negative 2. And it says to add it to whatever g of negative 2 is. All right, well, g of negative 2 is 4. So we get 3. F minus g at positive 2. F of g is, or sorry, f of 2 is 7. G of 2 is 4. F times g of 1, 1 is what I care about here. When x is 1, when x is 1, what's happening? So we have 5 times 1. Oh, hey, these are the same points from the function and in the graph form. And then they wanted to ask f of 0, f times g of 0. So now we have f of 0 is 3. G of 0 is 0. So it happens to be 0. And then, of course, they could also give us the actual equation version. And it looks like there's a typo here, and that's okay. It happens. So if they ask us to plug it in, we still do the same thing. We're going to plug in negative 2 to both these and then figure out what happens. So 2 times negative 2 plus 3, right? That's f of negative 2. That would give me, let's see, negative 4 plus 3 is negative 1. And then it says to add it to g of negative 2. And g says square negative 2. So I get 4. And surprise, it's 3. I have a feeling these are all the same as before. So we can plug it in here. 2 times 2 plus 3, we get 7 minus 2 squared is 4. So again, we get 3. Same thing with 1 and then a 0. Two plus 3 is 5 plus, no, sorry, times 1 squared, 1, it's 5. 2 times 0 plus 3, we get 3. Times 0 squared, which is 0, we get 0. So whether we do this from a graph or whether we do this from tables or whether we do this from equations, if they ask you to do the same thing, f plus g of negative 2, f plus g of negative 2, f plus g of negative 2, if it's the same equation every time, then you're going to get the same answers, right? It's the same method, whether it's from a graph or a table or the actual equation. All right, now let's talk about domain of each of these, okay? For the functions, f of x equals 3x squared, and that's supposed to be g of x equals 1 over x. Find the domain of a bunch of things. All right, so the domain of f of x. All right, so domain of 3x squared. Is there any number we can plug in there that causes a problem? Well, that's a quadratic, and no, domain is negative infinity to infinity. So that's all real numbers, no problems there. So we could write it like this. There's lots of different ways we could write it. We'll just do that. Left and right forever. G of x, remember from our graphing things real quick, it has no problems except for one spot. Remember, that's the function g of x, the graph of g of x. Where is this guy going to have problems? When the denominator is 0. So g of x can be anything, the x value there can be anything except 0. So we would just have to specifically state all x such that x is not 0. That's one way to write it. Or we could say negative infinity to 0, 0 to infinity. And so now if we start adding, subtracting them. Okay, so the domain of the sum, difference, and product is the domain of both f and g. Okay, so no problems here. We have a problem here. So we have a problem here. So the domain of f plus g is going to be where those are both defined. So this one was defined everywhere. F of x was defined everywhere. G of x had some problems. So everywhere except this problem is going to be the deal. X can be anything as long as it's not 0, right? And that's true for the difference as well of those two functions. X can be anything as long as it's not 0. The product, same idea. X can be anything as long as it's not 0. And then f divided by g. Okay, so now we have still the same restrictions that we had before. X can be anything except 0. But now we got to think, is there any way that g of x, we have to ask ourselves, is there any way that g of x would ever equal 0? So now we have to think about that, right? So we have to think, is it possible for this denominator of this fraction to ever equal 0? Well, g of x is 1 over x. Is that ever possible to equal 0? Can I divide 1 by any number and get 0? Nope, not possible. So we have no new problems then, no new restrictions. We still have the same ones we had before. Restrictions is what I meant to write. So we still have the restrictions we had before, which is x can be anything at once except 0. The same domain as both f and g. All right. It says write the expressions for all of those, assuming still that f of x is 3x squared and g of x is still 1 over x. Write the expressions for f plus g. Okay, well, f plus g. Done. That's cute. Easy. F minus g. Okay, done. F times g. I guess I should simplify that a little bit. That's really 3x squared. 3 times 1 is, 3x squared times 1 is 3x squared divided by x. Oh, one of those x's cancels out, right? Because that's, just as a side note, 3x squared is the same as 3xx. So if we're dividing that by x, one of those x's cancels out. So 3x and 3x squared divided by 1 over x. Now, this is when people start freaking out. We have fraction over fraction. And to clean this up a little bit, we're going to have to remember how you divide fractions. Okay. You take the first one and you leave it. You flip the one that you're dividing by and then multiply. Flip it and multiply it. Multiply by the reciprocal is another way to say that. So I flip that 1 over x, I get x over 1. Well, that's just 3x cubed. Divided by 1 is irrelevant, or inconsequential, I should say. Okay, so hopefully that kind of makes sense. You're just kind of cleaning things up a little bit and just doing what they say to each piece. All right, now composition of functions. A composition is when You have a function, f of x, but instead of sticking x in there, you stick another function in there. You stick another function in there, okay? And that's what this says right here. F of g of x. And the way that we read this, that little symbol, it looks like a circle. It's not a multiplication dot, it's a composition circle. And one way to read it is f following g or f of g of x. Or you can get fancy and say f composed with g of x or f of g of x. A lot of times you'll hear it say f following g of x. And what ends up happening is we call the guy that gets plugged in the inside function, and the guy that's farthest away from x, we call it the outside function. So let's make a little more sense of this, right? Example, if f of x is x squared and g of x is 7x minus 1. As a quick reminder, f of 3 is going to be 3 squared, right? Which is 9. F of a is going to be a squared, right? If I plug in anything in here, we're just going to square whatever that anything is, right? M plus 2. If I'm plugging in n plus 2, this function says take that and square it. Okay, so n plus 2 squared. And then, of course, we've talked a lot about getting good at n plus 2 squared. Simplifying that out, remember that's n plus 2 times n plus 2. And hopefully you're starting to memorize that if you FOILed all that out, you get the first thing squared, last thing squared, double the product. Okay. Now g of x, g of 3, 7 times 3 minus 1, which is 20. 21 minus 1. G of a would be take out the x and put an a. Well, I mean, if you clean that up a little bit, it's just 7a minus 1. And if we plug in n plus 2, 7 times n plus 2 minus 1. And then we just clean that up a little bit. 7m plus distribute that 7. And then combine our like terms. There we go. Okay, so now we have some different parts, but now this is where they're going to start making us do things where we put those two together. We put the f and the g together. It says to evaluate a composition function, g following f, we do a series of we're going to do a few different substitutions. So g following f means take out the x in the g and plug in the whole f of x function. Okay. So f of x was just x squared, right? So we take out the x and we put an x squared into g. Well, g said take that x squared and multiply it by 7, subtract 1. So let's do a couple examples. So that is g following f. Are you ready? This is going to make so much more sense here in a second. Oh, here's a couple more examples. You can read those yourself. Let me just do it to the side so it makes a little more sense. F following g of x is the same as f of x, but instead of doing x, we put in the whole function g of x. Okay, so f says do 6 times x minus 5, right? But we're not plugging in x, right? We're not plugging in x now. We're plugging in g of x. So I'm going to take this whole thing and pop it in here where the x used to be, 8 minus 3x. And then distribute and simplify things out. So 6 times 8 is 48. 6 times 3 is 18x. And then minus that 5. Combine our like terms. Negative 18x 48 minus 5 is 43. There we go. Now, if you'll notice, when they did the example, they put it in a different order, and those are both the same, just a different order. Okay. But what's interesting to me is if we switch the order that we do this in, if we do G following F of X, so G of F of X. So this time we're going to start with the G function, 8 minus 3, and instead of putting in X, we're going to put in all of F into there, right? The whole function F of X. And the whole function F of X is 6x minus 5. And then we'll clean it up. We'll see if we get the same answer. Let's see. Negative 3 times 6x is negative 18x. Negative 3 times negative 5 is positive 15. Combine our like terms. Negative 18x plus 23. That is not the same as what we got up here. So it is important to notice that if you do them, if they tell you to take f of x and plug it into g, and you accidentally do g of x and plug it into f, you're likely going to get the wrong answer. Odds are good you will get the wrong answer. Not every time, because there are some instances where f and g are a special case called an inverse. If you plug them in, it's okay in the wrong order because they're inverses, but most of the time they're not. So most of the time you'll get the wrong answer if you do it in the wrong order. And this is okay, let's say that we can just plug in f of x into itself. Okay, well, this is what it says over here. If we plug in 6x minus 5 into that, then that's saying 6 instead of an x minus 5. I'm going to plug in 6x minus 5 in here, right? And then we'll distribute 36x minus 30 minus 5. And of course, we get a different answer than we did a minute ago because we were asked a different question. Okay. All right. Let's just take in a function and plugging in another function. So here's an example. F following g of x, which is we're going to write down the outside function, f, and it says something squared minus 1. But instead of sticking x in there, we're going to plug in this whole g. So 3x minus 5 goes in there. My bad. Plus 5. Okay, now we got to remember how to square a binomial. And if you need to write it out and do the FOIL, you can. But I'm going to remind us, we want to learn some tricks and save us some time. So 3x, when I square that, I get 9x squared. 5, when I square it, I get 25. Multiply it together, so 15x, and then double it, I get 30x. And then, of course, that minus 1. 30x plus, I ran out of room. So 9x squared plus 30x plus 25 minus 1 is plus 24. Now, if we do it in the other order, we're going to take f of x and plug it into g. So let's write down that outside function with some space where we see that x so that we can plug in f into here. And f says x squared minus 1. So we have 3x squared minus 3 if we distribute plus 5. 3x squared plus 2. Again, same two functions composed in a different order gives you totally different answers, right? Totally different answer than this guy. Okay, another way we can show composition. And that's the way I was doing it. So, so now let's look at this. Okay, so now we've got this function and it has Q and S in it. But over here, we have a total different function that has q and y in it. It's not even the same letter. Suddenly there's a y, but there's still a q. So let's think about it. Which function is inside the other function? It looks like q got popped inside this y function, doesn't it? It looks like q is inside y. That's what it looks like to me. So we could rewrite, we could rewrite y. You say that 3 times fast. We could rewrite this, and instead of putting a q in here, what could we put in there? We could put in there what we said q is, right? We said that q is 15s squared cubed. That's what this says. Rewrite y in terms of s means make this function have an s in it instead of a q. All right, so then if we clean this up a little bit, -2 times 15s cubed would be -30s cubed. There we go. We're just plugging stuff in where they tell us to plug it in. That's the bottom line here. Now, decomposing means go backwards. We're going to start with some stuff that's stuck together and inside each other, and we're going to try and like peeling off layers of an onion. Almost like, if you've got a Tootsie Roll pop and it's like trying to get the Tootsie Roll out of the lollipop. Okay? So example, y equals this. We can think of this as the inside function and the squared being the outside function. Okay? So we do it on this one. Let's think about it. What could be the inside function here? I think maybe this little guy could be our inside function. So then our outside function is saying 2 divided by whatever m is. 2 divided by m. All right, let's do it again. Inside function, 5x minus 7. Outside function, the cube root of what we just called 5x minus 7, which we renamed it m. Decomposing can be a little bit trickier to see the patterns, but it's still not bad. And sometimes there could be lots of different ways we could do the same thing, decompose the same function. So we could say, for example, that the inside function here is x plus 3. And if we just say that the inside function is x plus 3, then the outside function would be 2 over m to the fourth, right? Or we could say the inside function is x plus 3 to the fourth power. If we include that fourth power in our function m, then y would just be 2 over that. Okay, so sometimes there's more than one way to do it, and that's just because there's more than one thing going on in here. Okay, the more